So yeah, I'm Ross Burton. That sounds weird. I'm the Meta ARM co-maintainer and the principal software engineer at ARM. So I split my time between working on Meta ARM and working upstream in Yocto. So my presentation is called "Why is my build so slow?" and what you can do to stop it. First, obviously, let's get the XKCD cartoon out of the way. Sometimes slow builds aren't always a good thing, as much as we may, joke about this. There are many aspects to what makes builds slow. Your build machine configuration is one thing, and also what is being built, what configuration, what recipes, for example. The most important tip is to always share your shared state and downloads directory. The only reason to delete any of these is if you're testing a build from scratch. You do not need a shared state per distribution or per machine. Multiple builders can share a shared state as directory as well. The public AutoBuilder has 30 builders, and they all access a single shared, NFS mount, which has the shared state and downloads directories on in parallel. As long as you've got a competent NFS server, which I realize is a bit of a stretch, this does work absolutely fine. If you're building inside a container, don't have those directories inside your container, because obviously every build you'll get a fresh one. I've seen CI systems fall apart because accidentally shared state was inside the containers that have thrown away every build. A CI that has to bootstrap GCC is not pleasant. Okay, so the first aspect of this presentation is going to be talking about the build machine. People often come on IRC and are like, "Oh, what's a good build machine?" And it's like, that's a bit of a vague question. The answer is the best you can afford. If you've got all the money in the world, go for it. But if you've got £500, then there are compromises you're going to make. It's quite possible you've got a laptop already. Maybe you've got your own, or maybe work's given you one. They work, but your normal laptop is not great at big builds. They don't have enough cores. They don't have enough cooling. They don't have enough memory. Storage isn't probably big enough or fast enough. I did a build on my personal MacBook Air just for a laugh when I got it. They are fanless, which is in normal use is absolutely fine. But I did have to balance it on pencils to keep the airflow up because it was firmly throttling really fast. So typically, desktop machines are a much better bang per buck. You can buy mobile workstations. They are more expensive and obviously are a lot bigger than a laptop. So, what are you actually gaining here? But we can look at some vague numbers. This is my very ghetto benchmark. It's just a fresh clone of Pokey. When these numbers were done, Kirkston was the latest release. Still RTS, so still good. Pre-populate downloads, because we don't care how slow SourceForge is. And then just time how long Sato takes to build. Really ghetto, just does its job. So a sort of generic corporate laptop costs about $1,500 of most currencies. 8 cores, 16 gigabytes of RAM. This isn't a terrible laptop. It's a nice corporate laptop. That took 2.5 hours to do Sato from scratch. It's not particularly great, but it's not. I've seen worse. Let's upgrade this to a mobile workstation. This cost about £3,000. It's got 16 cores, 64 gigabytes of RAM. It's a much better machine. 1 hour 45. It's faster, but it's not spectacular, especially when you're throwing that much money at a problem. This is portable, so that's your win. Or you could just go for a proper workstation. This is a workstation that we were trialing. It cost about £5,000, so yes, it's not cheap. 33 cores, 64 gigabytes of RAM, sort of huge amounts of NVMe storage. That did a SATO build in 27 minutes, which is a pretty good win. The I/O is just ridiculous. I deleted the build directory, then asked it to do another SATO build from shared state. It took 48 seconds. Just watching Bitbakes just stream through all the tasks was insane. So that was good. Obviously, you know, $5,000 per user is pretty pricey, but these are easily shared. You know, everyone's not doing builds all the time, so you could have a multi-user one in an office, or these make fantastic, you know, obviously CI machines. Throw a load of containers on it. So my build machine wish list. Lots of cores, but not too many cores. The compromise, if you throw too many cores at a system, is they tend to have a lower peak rate per core. So when you've got a single-threaded job, you don't want to be compromised there. You know, there are machines coming out now with like 80 cores or 100 cores, and if you look at the actual specs, the maximum rate on each core individually reduces as you gain. So you don't necessarily want that. Need good cooling. As long as it's a desktop system, you'll probably have decent cooling anyway. Plenty of memory. I'd say at least 32 gigabytes. If you're looking at anything involving C++, you will want more. And good storage. NVMe is just, you know, it's just a game changer. It's fast and cheap. I used to say to make builds faster, buy loads of RAM and do your builds in a temp FS, but NVMe is just as fast and cheaper now. So just do that. There's no gain to doing I've done some benchmarks, and there's zero gain in doing a build inside the temp FS compared to a decent storage these days. So just get loads. So now, assuming you've now got decent build hardware, we can look at what's actually being built and figure out if there's anything that's being built when it shouldn't be built, or understand where there are bottlenecks that you might be able to debug. So Bitbake has an option called graphviz, or -g, and that will dump out a dot file for the entire task dependency graph, which is vaguely useful, but quite verbose. It also dumps out a file called pn build list, which is a list of all the recipes it's going to build. That is very useful, because it's just a single file and it's nice and short. So you can literally just open it up in a text editor and just scroll through it and see if there's anything that stands out as being odd. Like GCC twice. A cross-compiler makes sense. My target is a 64-bit ARM machine, so here's GCC cross-arch 64. But GCC on its own is target GCC. So why am I building GCC for the target? There's a tool in OE core called OE_depends dot, which can poke at the dot files that have been generated and tell you what is happening. So you can ask it, why GCC? And it says, oh yeah, GCC is because of elfutils, and elfutils is in your image. So, okay. Elfutils is fine, because lots of pieces of software use that, RPM, for example. But, okay, so why is elfutils pulling in GCC? So if you look at the recipe, I can just quickly see that it's one of the rdepends for the ptest package. So obviously this package's test suite is deciding to compile some code, and it needs an on-target compiler. Okay, so now we understand the problem. You either suck it up and go, yep, I'm going to build GCC. Shared state cache hopefully won't make this too painful. But if you're not running these p-tests, which you probably should be doing, but if you're not, then you can just turn off the ptest distro feature, and you will drop a load of these dependencies. So elfutils putting in GCC, and there's other recipes which have some quite large dependency trees. If you're GPL adverse, GPL-free adverse, sorry, turning off ptest makes bash disappear a lot of times as well. Also, you may have a headless system with no display at all, and then suddenly notice that you're building libx11, which is unexpected if you have no display. So again, we can look at the depends file, and it tells us that Debus is putting it in. If you're using Debus, that's fine, but it shouldn't be depending on X11. So again, looking at the recipe, and it turns out that if the distro features has X in, then it pulls in the auto-launching of a server, which, if you're using a graphical system, is absolutely useful. But if you're not, then turn off the X11 distro feature. All these bits will just disappear. There's a lot of distro features. This is, at the time of writing anyway, the list of features in Pocky. Some of them are fairly useful, IPv6, but others, have impact on what you're building, and they may or may not care. So Vulkan, Wayland, ptest, OpenGL, debug infod. If you're not using these features, you can just turn them off, and you'll save yourself some build time. Pocky, always remember that Pocky is a vehicle for testing the Octo project and OE, so it turns everything on. You probably don't want everything on. Okay, so now that's quickly covered removing redundant recipes. So now we can look at the performance of a build and see if there's any interesting bottlenecks we could look at. This is where the buildstats class is really useful. This just monitors the build, and it writes log files telling you exactly what tasks were ran, how long they ran for, and what the processor utilization was at the same time. Really useful for spotting bottlenecks or other issues. Just inherit the class like you would normally, and do a build. Obviously, best if you do it with populated downloads, but no shared state. Ignore the first slide. So you can guarantee you have a complete build of everything from scratch. It writes files into a build directory. Human readable, machine readable, not particularly useful on their own. It's a load of numbers. But there are tools. We've got a fork of Piboot chart, which can read these files and draws nice time charts. So each task starts at the top and goes down, and time goes left to right. So you can see gaps where nothing was happening, or you can see that rate of change by how steep the curve is. So this is a build stats chart from the Workstation. Zoomed right out, so hopefully it's vaguely visible. It's got a steep gradient, which tells us that a lot of tasks are happening in a short amount of time. But there's some interesting regions, which you probably can't see, because I can only just about see them here. There's a big vertical yellow section at the top, which I've highlighted with the top arrow, and at the bottom there's a gap, which seems a bit strange. So if we zoom in, we can see this big yellow section is just a slew of tasks. Each task has its own color, and here, about 50 recipes all suddenly started to configure at the same time. If we look at the top, you can see that libtools do compile finished, and then everything else stampeded off. So this is, you do a bit of digging into the recipes. Discover this is Autotools bootstrapping itself. Once libtools finished, it can actually get on with running configure tasks for everything else that uses Autotools. There's not a lot you can do about this. Autotools is just slow to bootstrap, and it is. Things are getting better, but slowly. But at least, sometimes you just dig into it and you go, yep, that's the problem. Not a lot I can do about this. I will note that Mason had finished bootstrapping and was happily building stuff. At the top, very top, there's a Chemu build, which is built with Mason. So if you have lots of recipes using Autotools, then I do kind of recommend switching to Mason. It's just a lot faster and a lot easier to use. I'd like to say I'm not dissing Autotools, but I hate Autotools. So I am. Yeah. The other interesting region at the bottom, there's this gap. It's like, why is nothing happening here? Piboot chart hides very short-running tasks. So it's possible that there's actually like 1,000 tasks all running in that gap, and they're just all a microsecond long. Or something else is happening. So if we have a look, the purple task where it starts again is Rust native do install. Okay, so interesting. So if we scroll up a little bit, we find Rust native do compile, which is taking, on this workstation, 11 minutes. So it got to the point where this was the bottleneck in the build, and everything just waited for Rust to finish compiling. Luckily, Rust doesn't get rebuilt that often. It's native, so its dependencies are minimal. And it's better now than it was when these charts were done. But Rust is slow to bootstrap. And especially when people are threatening about, it's integrating into the kernel. More and more pieces are being written in Rust. This is going to be a bigger problem for us. There's not a lot to do here. There is talk about integrating a binary version of Rust into the build, just to avoid the bootstrap. The bootstrap can source for people who want it, but if you just care about speed, then you can just use the binaries. Yes, I'd say you might be able to find out what is using Rust and remove it. Unfortunately, librsvg uses it. So if you're using anything like graphical, which is GTK based, that's pulled in librsvg. If you're doing anything involving signed stuff, Python cryptography now uses it for reasons. So you might find that you'd have an annoying dependency on Rust, which you can't really avoid. So this is the boot chart from the laptop, the corporate laptop. It's a lot shallower, showing it took a lot longer. And there's still great big bars, so you can see Rust building. On this poor little machine, Rust took 55 minutes to build. But luckily, the Rust build was so slow, it didn't bottleneck anything. So, silver lining. One other useful thing that boot chart can do is show you the system utilization. I don't know why this didn't report the disk throughput. I think my mounting structure was a bit confusing. So the second row should be showing disk activity. But the top row is CPU usage, and then there's the yellow one is disk usage, and the bottom one is memory usage. This is really useful for seeing sudden spikes. So if you suddenly see a section where everything slows down and everything's maxed out, or all of a sudden the system crashes or builds break, you can see what's going on. Maybe, I need to throw more memory at the problem, or maybe I shouldn't have set number of threads to 60. And you can tune the system a little bit more. If I/O is turning out to be a problem, one interesting little tip is to use rmwork and then set the commit time on the file system to a couple of minutes. Let's do this on a separate disk, or at least separate partition, because if it dies, you don't want to end up trashing the entire disk. But if you build a recipe, install it, generate all the sysroots and stuff, and then delete it in under the commit time, it never has to hit disk in the first place, and you just saved yourself a load of disk time. Less of a problem now that people have decent storage that isn't really slow. But back in the days, if you've still got disks, spinning Rust disks, then this is actually quite useful. If system utilization is an interesting topic, then Random Cloud did a talk called Making Bitbakes Psychic, regulating builds using proc pressure. This will look at the current system load and decide whether it should do some builds or actually say, you know what, I need to run out of memory, all the processors are fully loaded, let's just wait a second. The AutoBuilder cluster uses this, and it's been really useful at leveling out the load, so the load builds are actually coming out faster, and you get less like random, intense spikes of memory usage, which normally end up causing failures. So we can also talk about optimizing rebuilds. Yocto's fairly unique, unlike most distributions. We rebuild recipes automatically. Most other distributions, you have to do it explicitly. This does have its advantages. We always know you can rebuild from scratch. Ask anyone who maintains a Red Hat derivative when they last bootstrapped their entire build and watch them squirm. And we always know the entire system can build from scratch. But the downside is that often you'll watch it building stuff, and it's like, why? Yeah, I know I changed this recipe, but why is it causing other things to rebuild? There are mitigations that have been added in the last few years. The main useful one is hash equivalence. This does require reproducible builds, but hopefully everyone's got that turned on. It's on by default in modern releases. Langdale onwards. Last time I gave this presentation, I tried explaining how it works, and it got into scary charts. Basically, the short version is when a recipe is built, it looks at the hashes of everything that came out and then compares it to what it has built previously. And if the inputs are different, but the output is actually the same as something else, then the system keeps track of this. And it can say, oh, I've built this before, I don't need to build anything else again. There's a more complicated version in the manual. So I did try explaining this last time, and it was quite complicated. But the end result is it can save a lot of time. So in this little example, I edited the autoconf native recipe. I put an echo into the do install. So it forced autoconf to rebuild. But the output is identical, because all I did was put hello world into the logs. So then I did a build, and it says that it wanted 970 odd state objects and missed all of them. So it started doing a full rebuild of the system, built autoconf native, noticed that actually I've done this before, and changed its unihash, which is the magic line saying I've seen this before. And then all of a sudden it says, okay, if I've built that before, then all these other things are still valid. So everything else can come from share state. So suddenly it says all these set scene tasks, all these share state jobs have become valid. Gets down to the bottom. I attempted to run 3,000 tasks, of which 3,000 didn't need to be run. So it's saved the entire rebuild. So basically, for faster rebuilds, make sure you use that. Turn on the equivalent hash and turn on a local hash server. It's awesome, and it mitigates almost all the problems that rebuilding everything from scratch causes. It's not enabled in the core by default, but Pocky does, so it's very well tested. The big caveat here is you need to share shared state between multiple. If you share the shared state between multiple builds, you also need to share a hash equivalent service to get full use. This is the Bitbake hash serve daemon. You just start one manually on your server. You can also have Bitbake read from a external hash equivalency server and shared state mirror, which is useful if you have a big centralized machine doing nightly builds. It can populate all the shared state and then expose itself. But we all know another machine which has a centralized read-only hash equivalency server and a shared state mirror, and that's the AutoBuilder. So if you're brave and you don't want to make house very angry, then you can tell Bitbakes to use the public AutoBuilder hash server and the public AutoBuilder shared state. And in theory, you can do builds from the AutoBuilder artifacts. At the moment, the server isn't on a CDN, so you will hit rate limits very quickly. And suddenly your fast builds are downloading at 30 kilobytes a second. But we have plans for this. But I have done experiments where you just restrict it to the native stuff. And that's a sufficiently thin slice, but you don't end up killing the servers. But it does make a massive difference because it pulls in Rust. So even if Rust is going to rebuild, so good. So useful. How am I doing for time? How am I doing for time? Bad. Lockshare, so it's really useful. There's a bug there. I'll skip over that because it gets confusing. Right. Yeah, so thank you very much. If anyone wants to talk about what Lockshare state objects are, then I'm around. It's a bit hairy. Or I'm on email, or I'm on IRC as Alberton on Yapto. Yeah, thanks very much. Any questions?